Have you ever stopped to think about what language a computer really speaks? I'm not talking about Python or Java. No, I mean its native tongue. It's actually a fundamental type of math, and it powers every single click, every search, and every line of code you write. Today, we're going to decode that hidden language, discrete mathematics.
All right, so here's our game plan. We'll start by figuring out what makes this the other half of math. Then we'll dive into the rules of truth with logic, learn how to organize, well, pretty much anything with sets, connect the dots using graphs, and finally, we'll see how this whole shebang powers the tech we use every day.
So let's kick things off with math's other half. We're about to get to the very heart of what makes this field so different and so incredibly essential. Really, the whole reason we're here is to answer this one big question. What's the mathematical architecture behind everything digital? I mean, the answer to this is the key to understanding computer science, AI, you name it. It's the structure of our modern world.
This right here, this shows the core difference perfectly. Over on the left, you've got continuous mathematics. Think back to calculus, with all those smooth flowing curves. It's the math of things that are, well, continuous. But on the right, we have discrete mathematics. This is the math of individual, separate, countable things, like integers, or the pixels on this screen, or the bits inside a computer. There are no in-betweens, just distinct units. And that is the world computers live in.
Right, so because computers live in this black and white world of separate values, they absolutely cannot handle ambiguity. They need a rock-solid system for reasoning, a clear set of rules for what is true and what is false, and that brings us right to mathematical logic.
You know, everything in logic has to start somewhere, and it starts with this simple little building block called a proposition. All it is a statement that you can definitively say is either true or false. That's it. Man is mortal is a proposition because, yep, it's true. The sky is purple is also a proposition because it's false. These simple true-false statements are the absolute atoms of how a computer thinks.
So what do you do with these atoms? You connect them, and we do that using logical connectives. Let's look at one of the most basic ones, the AND connective, laid out here in this truth table. The rule is dead simple. The combined statement A and B is only true if and only if A is true and B is true. If either one is false, the whole thing is false. This is exactly how a computer makes decisions when it has to check multiple conditions.
This is how we start building valid arguments, using what are called rules of inference, like modus ponens. Now, that's a fancy name for an idea you already use every day. It's just this. If A implies B, and we know that A is true, then we can be totally certain that B is also true. This simple if-then structure is the absolute bedrock of all programming and logical thinking.
Okay, so we've got rules for figuring out the truth. But the truth about what? We need a way to organize all the things we're actually talking about. And that, my friends, is where the powerful idea of set theory comes into play.
A set is one of the simplest yet most fundamental concepts in all of math. Seriously, it's just a collection of distinct items. Think of it like a bag of stuff where the order doesn't matter at all. The set of vowels is A, E, I, O, U, and that's the exact same set as U, O, I, E, A. For computer science, sets are the main way we think about grouping data.
And of course, we've all seen Venn diagrams. They're perfect for visualizing how sets interact. The union of two sets, that's the total area of both circles, is anything that's in either set. But the intersection, that sweet spot in the middle, that's only the elements that are in both sets. And this isn't just a classroom drawing, it's the exact logic a database uses. When you search for customers who bought product A and product B, you're telling the database to find the intersection of two huge sets of data. Okay, so let's recap. We have rules for logic, we have containers for our data. So what's next? Well, now we get to start building structures. Let's see how it all comes together as we connect the dots with graph theory.
Now, I want to be clear. When we say graph here, we're not talking about a bar chart from a spreadsheet. In discrete math, a graph is a structure made of two simple things: vertices, which are basically just dots, and edges, which are the lines connecting those dots. That's it. Dots and lines. It's an incredibly powerful way to model relationships and networks of any kind.
Just watch this. We start with our vertices, the dots. These dots could be anything: cities on a map, people in your social network, or web pages on the internet. Then we add the edges, the lines, which represent the connections between them, the roads, the friendships, the hyperlinks. And all of a sudden, an abstract mess of relationships becomes a tangible map that we can actually analyze.
So, this is the crucial part.
Why does any of this, the logic, the sets, the graphs, why does it actually matter? Let's bring it all home and look at the real-world impact.
Look, this stuff isn't just theory. It is the actual toolbox for building our digital world. That logic we talked about, that's the engine behind artificial intelligence. Set theory, that's the blueprint for every database you've ever interacted with. And graph theory, that's how your GPS finds the fastest route and how social networks map all your connections. Every single item on this list is powered by discrete math.
So, really, the ultimate takeaway is this. Discrete mathematics is the invisible scaffolding of our digital lives. You don't see it, but it provides the structure, the rules, and the language that allows our incredibly complex digital world to be built, to function, and to grow.
And that leaves us with one final thought. The next time you use an app, or you search the web, or you get one of those spooky good recommendations online, I want you to try and see the hidden machinery at work. Can you actually picture the logic, the sets, and the graphs all working together tirelessly just behind the glass?